Hi, this video is going to work through the Activity 5 for Module 6. The example we're looking at is called Looking Up to CEOs. In the book Blink, Malcolm Gladwell describes a study that investigated the hypothesis that male chief executive officers, CEOs, of American companies tend to be taller than the average height of 69 inches for adult American males. The study recorded the heights for a random sample of 50 male American CEOs and found that the mean height was 71.9 inches with a standard deviation of 3.7 inches. We want to test the researchers' hypothesis at the 5% level. So first of all, keep in mind the hypothesis that the researcher had is that the average height of male CEOs at American companies is higher than the average height of 69 inches among all American males. So the parameter of interest here is going to be the mean height among all American CEOs. We know that the mean height among all American males is about 69 inches. What we're interested in learning about is the average height of male CEOs and how it compares to 69 inches. So the parameter of interest it's the mean of a population, so we use the notation mu. It's the mean height among all male CEOs at American companies. Okay. Now, the null and alternative hypotheses. The hypothesis is that male CEOs tend to be taller than the average height. What we're trying to show evidence in favor of is the alternative hypothesis. So our alternative is going to be that the mean height among CEOs is greater than 69 inches. And the null hypothesis is going to be that male CEOs, on average, their height is no different from the average male in the United States. That would be equal to 69 inches. So this 69 here is our hypothesized value, remember. So now we need to pull out the sample size, the sample mean, and the sample standard deviation. The sample size, we have 50 male CEOs in the random sample. So we have n equals 50. The sample mean, the mean height was 71.9 inches. The sample mean, remember we use the notation x with a bar over it to denote the sample mean. 71.9. Excuse my crying puppy, 1 second. And the standard deviation for the sample is also given. The notation for the standard deviation, if the sample, remember, is s, and that's equal to 3.7 inches. Is it appropriate to use a t-test to test these hypotheses, and how do you know? Well, there are two sort of things that I need to think about. First of all, I use t when I'm testing a hypothesis about a mean, so yes, it's about a mean. The other thing I need to know is that the t-distribution is appropriate, and for that to be true, I either need to have a sample size that's 30 or more, or I need to be sampling from a normal population, or both. And in this case, since my sample size is greater than or equal to 30, and I'm doing a test about population parameter mu, the population mean, so yes, a t-test is appropriate here. Okay, now I need to calculate the appropriate standardized test statistic. The standardized test statistic for a t-test is t equals, it's my x bar, my sample mean, minus my hypothesized value mu sub 0, divided by my standard error, which is s over the square root of n. So substituting the values from our sample in here, we have 71.9 minus 69 was our hypothesized value from the null hypothesis, divided by S is 3.7 over the square root of our sample size, 50, and that gives us a value 5.54 as our value for our standardized test statistic. And we calculated this so that we can use it to find the p-value, measure the strength of evidence. But what is it actually measuring? If we look at this test statistic, we're taking the difference between our sample mean and the hypothesized value of the parameter and dividing by the standard error. So what it's really telling us is it's telling us how many standard errors away from the hypothesized value our value x bar is. So it measures the number of standard errors our x bar, 71.9 inches, is away from the hypothesized value of the parameter, which was 69 inches. Question 7 asks to sketch the distribution of this test statistic, assuming the null hypothesis is true, and shade the area that represents the p-value. Now when we are working with a t-test statistic, then it will, if the null hypothesis is true, have a t-distribution. T-distributions are symmetric and kind of bell-shaped and centered at 0. And in order to know which t-distribution we have, we need to know how many degrees of freedom there are. The degrees of freedom are equal to the sample size minus 1. In this case, that's 50 minus 1 gives me 49 degrees of freedom. To find my p-value, what I'm going to do is I'm going to take the value of my standardized test statistic, 5.54, and add it to my plot. And then I need to choose the appropriate tail to represent the p-value, the area in the tail. And the way I decide is I come up and I look at my alternative hypothesis. You can see it's a right-tailed test because of that greater than sign. So this area under the t-distribution out beyond 5.54 is going to be my p-value. Now to find it, I'm going to actually go to StatKey, and I'm going to need to use 5.54, my test statistic, as the cutoff. So here I am in StatKey. I'm going to use the theoretical t-distribution. I have 50 minus 1 is 49 degrees of freedom. And I'm doing a right-tailed test. So I click right tail. And now I need to change the cutoff along the bottom here to my standardized test statistic, 5.54. And my p-value is given here, 5.9 e minus 7. Okay, so my p-value is 5.9 e minus 7. This means 5.9 times 10 to the minus 7th power, which is 0.12345 zeros, 59. So there's my p-value. Very tiny p-value. Now what is the p-value measuring? The p-value, remember, is always measuring the chance of seeing a sample statistic as extreme as the one we observed or more extreme if the null hypothesis is true. So in this situation, that's the chance of observing a sample of 50 male CEOs of American companies with a mean height of 71.9 inches or taller if, in fact, the null hypothesis is true. The mean height among all CEOs is really 69 inches. That's what it's measuring. Now we can see that this is a very, very small chance that we'd see a sample like this if the null hypothesis was true. This is why we reject the null hypothesis. And our conclusion is going to be that there's strong evidence that the average height of male CEOs is in fact taller than in the general population of all U.S. males. Now, if instead of 50 CEOs, the sample had included only 30 CEOs, but had the same mean and same standard deviation, which sample would give stronger evidence against the null hypothesis? Okay, so quickly, just to kind of think about it, if we had a smaller sample of just 30, then our standard error, remember the standard deviation divided by the square root of n. So our standard error is going to get bigger. This means since we divide by the standard error in our test statistic, that our t-test statistic is going to get smaller. Dividing by something that's bigger gives us a smaller test statistic, which means we're not going to be as sort of far out away from 0 in our test statistic. Okay, so already it's looking like we're going to have a bigger p-value, right? The area is going to be bigger. It's actually going to be even more sort of extra bigger because of the fact that our t-distribution would also be having fewer degrees of freedom, which means there will be more area out in the tails than in one with 49 degrees of freedom. So we can see that our p-value is going to get larger. And that means that our evidence is weaker. With n equal to 30. We're going to finish up by making a 95% confidence interval for the mean height among all male CEOs of American companies. We're going to need to start by finding t-star and stat key. Okay, we go to the t-distribution. We still have 49 degrees of freedom because our sample was 50. And I need to put 95% in the middle, so I use the 2 tail. It already has 95% here, so my t-star value is 2.010. So there's our t-star. Now our best estimate for the standard error of the sample mean, standard error, remember, we're estimating with s over the square root of n. So we're going to put in 3.7 divided by the square root of 50, and that gives us a standard error of about 0.532. Now we're going to give the limits of the confidence interval for the mean height. To do that, we're going to use x bar, our sample mean, plus and minus our t-star times that standard error that we just calculated. Our x bar, remember, is 71.9 inches. We're going to add and subtract our t-star for 95% confidence, 2.010, times our standard error, 0.532. This gives us a confidence interval that goes from 70.83 inches up to 72.97 inches, and I'm 95% confident that the true mean height among all male CEOs of American companies is somewhere between 70.83 inches and 72.97 inches. Okay, so now we'll talk about the last question, number 15. Now the correct answer to question 15 is C. Less than 95% of male CEOs of American companies have heights that are contained in the confidence interval. Let's see why. Suppose this graph represents the distribution of heights among all American male CEOs, centered around the true mean height of that population, which we don't know, but will be centered there. It might not be symmetric, but we'll just pretend for now that it is. This same idea carries through regardless. So we can think of creating some sort of a range that will include 95% of heights for all of the CEOs. Okay, so now let's think about what the sampling distribution would look like for sample means of size 50. The sampling distribution is still going to be centered at the same population mean. It will be bell-shaped, but it's going to have less variability than among the individuals in the population, so we'll have something that looks more like this. Now the width of the confidence interval is based on the variability here, so we give an interval that's basically wide enough to contain 95% of the sample means. However, you can see that if we take this same width and carry it up into our population of all CEOs, that it's no longer wide enough to have 95% of CEOs. In fact, it has less. So it's because there's more variability among individuals in the population than there is in sample means that the confidence interval is not going to be wide enough to get 95% of CEO